Hi everyone, I'm Candice Majewski and I'm an academic at the University of Sheffield. And for today's talk, I'm going to talk to you a little bit about some of the work we've been doing on introducing antibacterial capabilities into some of our 3D printed parts. So the background to this specific work was funded through the EPSRC Bright Ideas Awards. And so in this case, they were asking for potentially transformative projects that had the potential to contribute to some of their stated outcomes, which I've listed there. Before I get into any of the detail, obviously there's a lot of people involved in any of this type of research. So Bob Turner was a postdoctoral researcher on the project while it was running. James Wingham is a PhD student within our group who's also part funded by the EPSRC, and his PhD is ongoing alongside this. Joey, Jason and Tom from our School of Clinical Dentistry, and then Wendy Bertwasaw, who's a member of technical staff in my department, which is mechanical engineering. So the overall aim of this project was to bring antibacterial properties into specific types of 3D printed parts, in this case polymer laser sintering, and I'll talk a little bit about that in a minute just for any of you who aren't familiar with the process. And we were really coming at this from a perspective of wanting to address some of the ongoing issues around antimicrobial resistance, but we also wanted to see what we could do to make our parts work harder, if you like. So how could we bring some extra functionality into our parts, take advantage of the geometric capabilities of 3D printing, but also do something extra as well? And it was also quite a good fit with our EPSRC manufacturing hub, which I've linked to there if anyone's interested, which is all about powder-based manufacturing processes and trying to help powder-based manufacturing reach its full potential. So in some cases, that's to do with the repeatability of our parts, the ways in which we can use them and so on. In other cases, it's more simply saying, actually, we're not yet at a stage where we're getting the best out of these parts. So they're not doing everything they could be doing. And you know, in some cases, we're not working them as hard as we might. And I'm guessing the idea of antimicrobial resistance is probably known to quite a lot of you watching. This quote from Dame Sally Davies on Tomorrow's World really struck home when she was talking about the numbers of people that are affected by this. So we know that we have a global problem with antimicrobial resistance. We also know that we need antibiotics for certain things where we can't at the moment eliminate them. So surgeries, chemotherapy patients, and so on. So there's plenty of reasons why we would want to reduce our reliance on antibiotics. And so this was just from the AMR review I've linked to there. This was just an example of some of the things that might be approaches to overcoming these problems. And so we kind of had a look at that and said, actually, there are things that we think we can do that will help in some of these areas. And so what we're particularly interested in is preventing the spread or reducing the spread of bacteria through contact with things. And obviously that's been in the news quite a lot recently with the COVID-19 situation, but even before that, we know that we get lots of spread of infections through contact with things. And we also know that there's a lot of processes in place, standard procedures. So, you know, we might coat something with an antimicrobial coating. We'll have certain sterilization or cleaning procedures. But what we also know is these have disadvantages inherent with them. So human error can be a thing. If someone's busy, rushed, they're trying to go through the processes they need to, that can be an issue. Cleaning procedures can be stated and followed, but may still be ineffective in certain cases or not cover anything. And one of the things we're particularly interested in is if you look at coatings, the idea that if you get a scratch on a coating or you get some damage within the part, you can actually end up kind of producing new surfaces, if you like. So in the examples shown there, we've got a crack and a scratch, but where the coating that we've put on is now gone effectively. So we've reduced that level of protection in that area. We're making it an area which is more likely to then become an issue later on. And when we looked at this project in the first place, there were obviously clear kind of medical and healthcare applications for this. But what we can actually see is quite a range of applications we might find use in. So all the way from consumer goods, I've used the example of mobile phones there because we kind of have them in our hands all the time and we're walking around with them, we're putting them down in places and so on. And then kind of working up through the kind of level of shorter term, less specialist things or more consumer focused products, all the way up to the medical side. And obviously the medical applications are a clear area of potential impact, but quite a way further off down the line in terms of qualifications and getting them into practice. So the approach we're taking, we take standard laser sintering polymers. As I say, I'll mention what laser sintering is in a minute, but we take a standard material for the 3D printing process and we combine it with a silver-based additive. And so when we were researching this, we know that silver has antibacterial properties. We already know it's used in quite a lot of antibacterial settings. And so we thought that was a really good starting point for the work we were doing here. What's quite interesting is when you get into the research behind it, we still don't actually know exactly what's going on. So we don't understand exactly why silver is so effective or all the mechanisms by which it works, but we do know that release of silver ions is quite a key part of it, and we'll come to that in a few slides' time. So as promised, laser sintering is one of the group of 3D printing processes that we have available. So it works in the same way as any of the other processes. Take your digital file, slice it, and build those slices one at a time. And in our case, we're taking a layer of powdered material, and specifically in this case, a powdered polymer material. And we scan a cross-section of that with a laser. Melt the material in the cross-section that we want, deposit another layer of powder, scan again for the next cross-section, and carry on until we've built our parts. And there's a couple of reasons we're particularly keen on this. So for those of you familiar with processes that use support structures, in the case of polymer laser sintering, we don't need to do that. So the loose powder surrounding our cross-sections acts as that kind of support for overhanging areas. So that means we can do some more complicated designs and assemblies a lot more easily. And another potential benefit there in a lot of cases is because we have this powder acting as a support, we can then produce our parts throughout the build volume. So we're not restricted to producing parts on a single layer. And so that can give us benefits in terms of the time and cost of producing our parts. So we chose the process for a couple of reasons. One is there's a lot of interest in polymers for a range of applications, partly because of this geometric complexity, but at the same time, being able to do more complex geometries and shapes, and especially internal geometries, actually gives us a potential issue in terms of the ease of cleaning or coating these items. So we solve one potential problem through geometry, and we're potentially creating a more difficult solution or a situation there as well. And we specifically chose laser sintering because of the powdered polymer processes available. It's the most well documented. It's also the least complicated process. So we thought we'd start with that because it's the easiest way to identify whether our approach is having an effect and then move on to other processes later on. A couple of specifics. So we selected nylon 12 as our base polymer, and that's simply because it's the most repeatable, the most well documented material for polymer laser sintering. And so what that allows us to do is say we can be reasonably confident that any differences we see with and without the additive that we put in are down to the additive. So it's not just lack of repeatability in our system. And we took a silver phosphate glass as our antimicrobial agent in this case, which was already being used in antibacterial powder coating applications. So that allowed us to take a polymer that we know works well in our process and an antimicrobial agent that we know already has been proved in certain situations. And in our case here, we literally in the first place took the two materials, mixed them together, so mainly the polymer and a little bit of the antimicrobial additive, mixed them together, which is quite simple and quick as long as we can make sure we mix them effectively. And again, we'll talk about that in just a few slides' time. So I thought what would be really interesting in this talk would be to give you an idea of the kind of stages that we have to go through when we're trying to look at different materials within our process. It's definitely not as simple as take the material and stick it in the machine and it works. And so we kind of had this really set list of criteria that we needed to go through to kind of prove each stage. And I'll go through those briefly now. So the very first question was, does it sinter? So does it work when we put it in our laser sintering machine, this combination of the material, the polymer material and the antimicrobial material, does it work? So is there anything that goes wrong during the process? Does it affect our ability to make parts? So does it sinter? Yes. So this was actually, despite the fact that all we've got there is a few very simple geometries. So on the left, you've got a standard nylon 12 with no antimicrobial additive, and on the right, you've got the same polymer with the antimicrobial agent put into it. So that's a big point for us because actually if we can get past that stage, we know that we're kind of going in somewhat the right direction, at least from a manufacturing perspective. So then the next question for us is, do we have any effect on our mechanical properties? And in particular, do we add this material into our polymer and then reduce our mechanical properties in any way, which we'd normally want to avoid? So another bit of good news for us. So on this graph here, we've just got the virgin or the standard nylon 12 and the nylon 12 with the additive in it. And you can see those graphs basically all overlap with each other, no difference. And if you want to see the numbers again, so these are the main tensile properties that we record, and you can see that we're not showing any significant effect on our properties. So we can say that at these relatively small amounts of the antimicrobial additive, we're not negatively affecting our mechanical properties in that way. The next thing we want to note is, do we get a good dispersion of the additive within our parts? So this comes back to the fact that we're mixing the two materials together to give us the material that we're using for our tests. And we want to be sure that we haven't just got a clump of the antimicrobial additive in one area and nothing in the rest of the parts. So we first of all had a quick check to check that we actually had the silver content in the parts that we were expecting. So make sure that we hadn't somehow destroyed that material during the laser sintering process. You'll see there we expected from the datasheet values and the amount of the additive that we'd put in, we expected around about 190 milligrams per kilogram. We ended up measuring about 113 milligrams per kilogram. So a slight difference there, but in the right ballpark, that we could be confident that we had at least some of the material in there and hadn't really negatively affected it. And we've also been looking at the interior of the parts, so we can use micro CT quite effectively, and we do that quite a lot within 3D printing areas. And in this example here, this is just a slice of one of the parts that we made. So the grey area, so the majority of the material is our base nylon 12, so that's the material that the polymer material we'd normally use as standard. You'll see these black areas, which are pores or holes within the parts. So we tend to not get a fully dense part or a fully solid part. We'll quite often get some porosity in it. So we can see that through micro CT as well. And then the really good thing for us in this case is these little white bits that you see in it are our silver-based additive. So we can see those in the images, and when we did some analysis on the numbers, we could see that the additive was well distributed throughout the part. So we're confident that actually just by the simple mixing process we did for our material, we were still getting good dispersion within the parts themselves. And I mentioned we know that the release of silver ions is important in this case to achieve the antimicrobial properties. So the next thing to do was check that it does. So you'll see a very logical progression of steps at each place saying, you know, is this a stopping point for this work? So does anything categorically go wrong at any stage, which means there's no point carrying on. And so in this case, we were just taking some little 1 centimeter cube spheres, measuring them over a period of a week to see what was happening and were we getting release of the silver ions. So we can carry that on for longer periods of time as well if we want, but basically we wanted at this stage to see that something was happening and that we were getting those silver ions released from the parts. So up till this point, that's all really good, and that kind of covers us from the manufacturing process, being certain that what we've got in the parts is what we expected to get. Fairly obviously, if we're talking about things to do with human contact, we want to know, is there a problem with that in terms of harming human cells? So Jerry, who's our microbiologist on the project, did some work looking at that to see, do we get any effect of adding this into the nylon 12? Do we see any negative effect on human cells? The answer was no from those preliminary results. So again, at each stage, we're kind of building up the potential for showing that we have a good concept there. And so the final point, and this is the kind of the initial work that we've got to at the moment, how do the parts interact with bacteria? So everything and all the evidence in the literature suggests that this should be an approach that should be able to work, but obviously we need to see that in some kind of practical sense. So I've included a link there to the recent paper that we put out on this, but what I really wanted to show you on this chart was If we take the same bacteria and we put them in different test media, so a very nutrient-rich material on the right, so that's the BHI material, where we don't see much of a difference between the standard nylon 12 and the nylon 12 with the antimicrobial agent in it. But then when we come to a less nutrient-rich media, we find that we do see a significant benefit in including the antimicrobial additive. And so that's quite interesting for us, because what it says is there's a lot more work to do there to understand exactly how this approach is effective and how we can get it to work in different situations. And so we've done a little bit more work on that as well, just looking at the neat antimicrobial agent in different test media again. And so we're starting to try to understand why we see these different results in the case of the different media. And that's about as far as we've got with that at the moment. But obviously, if people have comments or thoughts on that, that would be really interesting to hear. And just finally, to go into what we think the next steps are. So one of the things we're just starting to think about is this idea of test conditions. So how do the parts behave in certain test conditions, but actually how can we replicate real life situations? So if we're talking about bringing things in the future into kind of real life situations, how do we make sure that our parts are going to perform in those specific areas? We're also looking at things like varying the concentration of the additive. So, if we put 2% of it in rather than 1%, do we get a subsequent benefit? Do we do anything wrong to our manufacturing process by doing that? And also coming on to other materials, so the base polymers, but also the antibacterial additives. We might look at other materials that have known antimicrobial properties. We might look at the concentration of those additives as well. And also things like we're starting to think about release rates of the material, or of the silver ions in this case. So looking at whether or not we might want situations where we pop out a load of silver ions really quickly, or other situations where we just might want a more gentle release over a longer period of time. And if everyone could keep their fingers crossed, we have a couple of funding applications under review at the moment to start looking at very specific test cases. So specific products or devices that are currently used in a healthcare setting to see how this approach works or doesn't work in those situations. So I think that should be about time for me. I will stop talking now, and I think there's probably a few minutes for questions, so I'll hand over to the chair for that. Thank you very much.